Hello, hello, hello. How are we this fine afternoon? Hi, who do we have? Is anyone there? Hello, hello, hi, hello. Oh, you're gonna make me do these calculations by myself. Wow, wow. I mean, I will, because I love quantitative chemistry just that much. Hello, hello. Yay, natural scientist. Hi, I remember you. How are you? It's been a while. How are you doing? It's been a minute. I'm glad that you're here. Thank you for joining this afternoon. Do you have your calculator ready? Okay, glad to hear it. Hopefully you've got your calculator because today, as you can see from the title, hi Brandon. Yay. Okay. Hi, hi, hi. Hi. We are going to be doing some chemistry calculations today. Hi, Yusuf. Okay. Yay. Anyone, any more for any more? Anyone else want to say hi? Anyone else? I mean, I'm not scary, I promise. I promise. Okay. Thank you for tuning into our MES MyHeadspace trial lesson today for year 13. So we're going to be doing some calculations practice because this is one of those topics, right? And just to check, are you all starting or just started year 13? Hi, Denny, welcome. We've all just started year 13, or maybe there are some of you that are in year 12, who knows? But amount of substance, lovely, amount of substance, so your calculations, your quantitative chemistry, this is one of those topics that crosses over multiple topics across your A level. So it's so important that you feel super confident in this particular area so that you can apply it across the board and get those like marks for those chunky calculations. So before we get started properly, if you know anyone that you feel would benefit from this free trial calculations lesson, they're a year 13 or maybe even a year 12 chemist, then just copy and paste the link, right? Share it with them. Don't gatekeep, right? Let's have as many over here as possible. Okay, so can you all share this link with, let's say, at least one other person? Maybe put it in a group chat so that we can have some more kind of helping us out with our calculations today. And then I won't have to call on you quite so much. We'll be able to share the load a little bit. Okay, I'm going to give you a moment to do that. Thank you so much. Thank you so much. Partition coefficient, that, ooh, is that chemistry? Denny, what topic is that in? Hi, Tanya. Yay, welcome. Okay, so hopefully you've all shared this link with somebody, someone that you want to help out, or someone that you know kind of needs that little bit of extra help with their chemistry A level. I'll do a quick introduction in case you don't know who I am. KP. So I will have, yeah, KP and KC will be covered as part of our main course. Let me just quickly introduce myself. I'm LaJoy. Hi, LaJoy Tucker. I am, of course, a chemistry teacher at My Headspace. I studied chemistry at Oxford University. So I did a 4-year undergraduate master's degree and I got a first. Let me just, yeah, yeah, yeah. And I have been teaching, it says over 10 years. This is now my 12th year of teaching. So you are in safe hands with me. I have been teaching chemistry A level. I've taught chemistry IB, and I love teaching chemistry at those high levels and helping students get those top grades. So I hope that you stick with me at least for this lesson, and if not longer. Hi George. Good question. Let me just double check the timetable for you. And I'll do more of that information towards the end, like more details about the course itself. But for year 13, it's 2 lessons a week. The lessons are an hour and a half each. And the lessons are on, let me just double check. My lessons are on yeah, Mondays from 7:10 and Wednesdays from 7:10. So Monday and Wednesday evenings for year 13, chemistry AQA. Chemistry OCR, I think, is also on the same day. So we've got 2 year 13 courses. We have an AQA course and we have an OCR course, which is taught by my colleague Devinda. Dav does chemistry. So, you know, you can find something that fits depending on which exam board you're on. If you're taking Edexcel, then we don't have a specific Edexcel course at the moment, but the OCR course is probably the most similar to that one. You're very welcome, George. Okay, any other questions before we get into the chemistry? And again, don't forget, share this video. It's free. It's just on my YouTube channel. So if you just copy and paste the link, send it on, and then we can have more to do some quantitative chemistry with us. Do we have our calculators ready? I've got mine. My calculator is, oh, this isn't my broken one. This is a decent calculator. Okay, are we ready to get started? Let's get started with just the base concept of moles, right? Because moles will underlie all of this. Hi, Toby. To be fair, we do moles in year 11 as well, but this is going to be just the extra little bit of challenge. Oh, natural scientists, it depends on what type of questions. So when we're talking about moles, the mole is essentially a unit of measurement for the amount of substance. So 1 mole of any substance contains 6.02 times 10 to the 23 of its units. What name do we give this value? Oh, wait, it's on the screen. Never mind. Spoiler alert. We give this value the name Avogadro's constant, right? After Avogadro. Which is lovely. It's essentially a number of particles. So 1 mole of particles, 1 mole of any type of particle will contain, thank you, natural scientists, 6.02 times 10 to the 23 of those particles. Okay. Now, as we know, there are different ways that we can calculate moles. And I always say, anyone that's been in any of my lessons before knows that something that I say the most often is, for these calculations, when in doubt, moles, right? If you're ever not sure how to approach a calculation, then I strongly recommend just starting off by calculating the number of moles and then going from there, right? I said it so much that my year 13s a couple of years ago actually made me this hat. Okay, that's how important it is. So to start off with, I would like you to tell me all the different ways that you can calculate moles. Lovely. Oh my gosh, natural scientist is on it. So we can start with number of moles, and I'm going to use the letter lowercase n for moles. So moles will be equal to the number of particles divided by Avogadro's number. Lovely. Or Avogadro's constant, depends on what you want to call it. Okay, now number of particles, we usually give the letter capital N, and then Avogadro's number depends where you're looking. So natural scientists, you're absolutely right. Na is sometimes given, or if you're doing AQA, usually the letter that they use is L. I actually don't know why it's L, but that's the letter that they use for Avogadro's constant, or N subscript A. Thank you, Tanya. Okay, next we've got, thank you, Brandon. We can use, if we're dealing with solutions, then the number of moles is equal to the concentration multiplied by the volume. And units, of course, very important here. Units for concentration, typically moles per decimeter cubed. And then our volume needs to be in decimeters cubed. More on that in a bit. Oh, natural scientists. Now, we don't use this calculation in AQA, but I'm going to put it there anyway. When we're dealing with gases, if we are at a particular temperature and pressure, and we know the molar gas volume, we can say the number of moles is equal to the volume of that gas divided by the molar gas volume, which is the amount of space that 1 mole of any gas takes up. Now, at room temperature and pressure, that is 24 decimeters cubed. Again, this is not AQA, this bit. So if you're seeing this and you're like, I've never seen this before, oh no, please don't worry, okay? You typically see this OCR and Edexcel, but not at AQA, okay? More commonly, what expression will we use to calculate moles if we're dealing with gases? What expression do we use to calculate moles if we're dealing with gases? Anyone? Thank you, George. The ideal gas equation. So we'll use PV equals nRT and then rearrange to make moles the subject. Moles are equal to PV over RT. We're going to get more into the units of that as we start to go into our practice questions. Lovely. Okay, Sorry, my green screen is really misbehaving today. Do we have any others? Is that about, oh, the first one that we learn? Everyone was so fancy. No one's told me the one that you learn already just in GCSE. What is the most standard way that you would calculate number of moles? What's the first way that you learned to calculate moles? Thank you, Brandon. Moles are equal to mass divided by MR, or molar mass. Great. What should the units for mass be in these instances? What should the units for mass be? Mass over MR, sometimes mass over M. Thank you, Brandon. Mass in grams. Great. And then MR technically doesn't have units, so it's a little bit weird like that. Lovely. Now that we've got that out the way, hi RJ. Now we've got that out the way, let's start to put this into practice. So we'll start with some like quite straightforward moles calculations, and then we're going to try some trickier ones, right? I want to kind of start to make you feel a bit more confident, a bit more comfortable with some more challenging calculations. So let's start here. If I asked you how many moles of water molecules are there in 180 grams, well, as you've all told me, if we've got mass in grams, then we're going to use the expression moles are equal to mass over MR. Our mass directly from the question, 180 grams. Our MR, where do we get that from? Remind me. How do we get the MR? Natural scientist straight in there with the final answer. How do we get the MR? Where does that come from? Oh, George, that's for carbon dioxide. So I know there are probably a couple that you've learned already. Yeah, that's carbon dioxide. For water, H2O. Looking at your periodic tables, which I know you've all got painted on your walls. Thank you, George. 18. So 2 for hydrogen and then 1 for oxygen. Lovely. So we know that we've got technically 18.0, right? Because your MRs in your A-level periodic table are all to one decimal place, but we can say we've got 10.0, 3 sig figs, yeah, 10.0 moles. Lovely. Let's go to the next one. How many moles of oxygen atoms are present in 44 grams of carbon dioxide? Hi, Theo, welcome. So where should we start? How many moles of oxygen atoms are present in 44 grams? Yes, absolutely. We're going to start, when in doubt, we're going to find the moles. And we've got enough information to calculate the moles of carbon dioxide, mass over MR, 44 over 44, which is 1. But that's not the question. Hi, Prisha. Hi, Ads. We want the number of moles of oxygen atoms. So then what do we need to consider? We need to consider that in every one carbon dioxide molecule, there are 2 oxygen atoms. So the number of moles of oxygen atoms will be 1 times 2, which is now 2 moles as our final answer. Are we happy with that? This is just our training. This is just us getting ready for the real calculations coming up. Lovely. Natural scientist has spotted what's going on for question 3. How many molecules in 2 moles of water? If we're asked for the number of molecules or the number of ions or the number of atoms, etc., we know here we need to use Avogadro's constant, right? We're going to need to use L/Na, depending on what you want to call it. So if we have got our molecules, that's our N, number of particles, equal to our number of moles multiplied by Avogadro's constant. So 2 times 6.02 times 10 to the 23 gives us, what's that? 1.2, where's my calculator? 1.2 something. Thank you. I still want to give it to 3 significant figures just to be consistent. So 1.20. Thank you, Brandon. And thank you, natural scientist. Great. Are we happy so far? Do we feel nice and warmed up? Do we feel nice and warmed up here? Give me a yes, give me a no, give me a maybe so. If you've got any questions at any stage, please do ask. There is no shame in asking questions, getting clarity. It's better that you ask the question. I'm sure somebody else is thinking it if you're thinking it. to make sure that you feel super confident with this. Are we all good? Are we? If there are no questions in about 10 seconds, I'm going to count that as a yes. But if it's taking you a little bit longer to type your question, please do still type it, and I will get to it. I'm so sorry. My green screen is running away from me. And I will get to it in good time. Okay, let's go to our main questions now. And our questions are based on what we call stoichiometric relationships. Now, that is really kind of a fancy way of saying molar ratios, right? Because we use stoichiometric relationships, we use the coefficients in balanced symbol equations to tell us the ratios in which different species are involved in a chemical reaction. So the ratio in which reactants react and products are formed. And those coefficients are these numbers in, well, the letters in blue. Okay, so for example, the ratio between A and B is A to B. Are we happy with that? Again, I'm going to take it as a yes unless there are any questions, but please do ask questions if you have any. Okay, so question number one, nice and straightforward. This is more kind of GCSE-ish style, but still important that we get to grips with it. What mass, exactly, George, exactly that. So what mass of carbon dioxide is produced when 4.60 grams of butene is burnt or burned? Where do we start? Let me reach over and get my cap. Where do we start? When in doubt, when in doubt, moles, right? And we're going to start by calculating the moles. Thank you, Brandon. Thank you, RJ. We're going to start by calculating the moles for whatever we can calculate the moles for. We have got the mass of butene, so that's what we're going to start calculating the moles for butene. Oh, that's a weird H, which is going to be mass over MR. Our mass, 4.60. Our MR, we might want to do over at the side, or we can put it all in, it's up to us. That's going to be 4 times 12 plus 8 times 1. 48 plus 8, 56. Can I count? I hope so. Am I out of practice? Yeah. 56, which gives us for our moles. Feel free to give me the answers in advance if you get them before me. 0.082 moles, okay? Notice, so important, and I want to really highlight at the moment, it's so important when you're carrying out these calculations that there are no floating numbers, okay? Every number needs to belong somewhere. It needs a label. It needs to belong somewhere. And that's for multiple benefits. It's so that you can track your calculation, right? You know what's happening at each step. And whoever's marking your paper, right, can track what you're doing as well. Because mistakes happen, right? I still make mistakes. But if you're laying everything out and you're labeling what all of these values mean, it's going to be a lot easier to spot these mistakes than if there are just random numbers written all over your page. Okay, so it might take a little bit longer to get started, like to practice laying out your calculations, but it is definitely going to serve you in the long run. Okay, now we've got our moles of our butene. We need to relate that to the moles of carbon dioxide. How are we going to do that? Well, we're going to think about our stoichiometric relationship. So the ratio from butene to carbon dioxide. What is that ratio? What is that ratio? I'm seeing some combined values, but I want to make sure that we understand it step by step before we start kind of skipping steps. 1, 2, 4. Right, thank you, Prisha. So there's for every 1 butene, we make 4 carbon dioxides. So that means in order to get to our moles of carbon dioxide, we're going to take our moles of butene and we're going to multiply that by 4. Now, even though that's the number that I'm writing down on my page, in my calculator, I'm not losing any of these numbers, right? It's ants, and just keep the values and only round right at the end. So you can round on paper, but don't round your final answer until you've got to your final answer, right? So 0.329, 0.33 moles. Okay, let's do 329. Now we've got the moles of carbon dioxide. Of course, we want the mass of carbon dioxide. Lovely, which is going to be moles times MR. So that's our answer we've just got, keeping everything in our calculator, multiplied by 44, our MR that we figured out earlier, and we get, I agree, thank you, 14.5 grams. Now, this, I didn't say specifically in the question, give your answer to an appropriate number of significant figures, but this is 3 significant figures here, and that is the most appropriate. Why is this the most appropriate number of significant figures? Who knows? Why is this the most appropriate number of significant figures? Anyone, anyone? And it's not just because it's 3 and it's always 3, because it's not always 3. How do we decide? How do we decide? Let me get my highlighter out. If anyone wants to make a suggestion, who knows? Or wants to take a guess, an educated guess based on what they can see on the screen. Thank you, RJ. It's based on whatever values we've got in the question. So we give our answer to the same number of significant figures as whatever the least number of significant figures are in the question, okay? Here, we only had one value in the question, which was the 3 significant figures. So that's automatically the least. So that's what we'll give our answer to. If we had multiple values, and we'll see that later on, and they've got different numbers of significant figures, we give it always to the least, because we can only be as precise as our least precise measurement. Is that clear? If that's not, please, please, please let me know. But as we do some more examples, hopefully it will become clearer. But if that's just, you've got no idea, please let me know. Least number of significant figures in the question. That's what you give your answer to. That is the appropriate number if they ask for an appropriate number. Sometimes I'll just say, give it to this number of significant figures. That's fine. If they say appropriate, that's what they mean. Are we happy with that? Yes, LaJoy, we're very happy with that. Oh my gosh, wonderful, fantastic. This is what happens if you don't talk to me, I start talking to myself. And then I look like a weirdo. So please, please help me out. Okay, are we ready for question 2? Are we ready for question 2? We're gonna step it up a notch. Each question, we're gonna do that. Okay, thank you, thank you. Okay, question 2. Potassium dichromate reacts with iron 2 ions in an acidic solution according to the equation blank. 1.00 grams of potassium dichromate reacts with excess iron 2 sulfate in sulfuric acid in 100 centimeters cubed. Calculate the concentration of Fe3 plus formed. Now there's a whole bunch going on, but when in doubt, even if they've given us a ton of information, where are we going to start? When in doubt, where will we start? Thank you, thank you, thank you, moles. And we're going to calculate the moles for whatever we can calculate the moles for. At the moment, based on the question, we've got enough information to calculate the moles of the potassium dichromate, so that's where we're going to start. Because we've been given the mass and we've been given the MR. What do we have? Again, if anyone gets to the answers before me, please let me know. Although I have trust issues, so I'll probably still check. It took me about half a year to start to trust my like my year 12s and my year 13s last year to just give me the answer, and I just didn't check because I was like, you know what? I have trained you well enough now that I know I can trust in your answers. But I'm just meeting you guys, so forgive me if it takes me a minute. Okay, that's our number of moles of potassium dichromate. Now what? we're going to, of course, look at our molar ratio, our stoichiometric relationships to figure out how many moles of Fe3 plus that relates to. Okay, now we don't need to worry about the iron 2 because the iron 2 is in excess, which means that our the amount of product we can make is only dependent on our limiting reactant. So our moles of Fe3 plus, lovely, thank you, RJ. We're going to look at our ratio, which is a 1 to 6 ratio. So we're going to take our moles for our dichromate. We're going to multiply that by 6. Wonderful. And of course, I'm keeping that answer in my calculator. So I'm not just writing that number down again. I'm just keeping everything as we go. And we get 0.0204. Let's do that. Okay. Now we've got moles. We don't want mass this time. The question has asked us to calculate the concentration. So how are we going to calculate the concentration, which I'm going to do as square brackets like this? That's what concentration is. Or we can write C, Fe3 plus, up to us. Same. How will we calculate the concentration? Thank you. Moles over voles, right? Moles over volume. Fantastic. The moles we've already got. The volume, what are we using for the volume? And this is where we have to be careful. What are we using for our volume? Thank you, George. We need to convert our volume to decimeters cubed. So we're going to take our 100 centimeters cubed, divide that by 1,000, and then we get 0.1 decimeters cubed, and then that's what we're going to put into our expression. And we get, what's that? 0.204 moles per dm cubed. Is that an appropriate number of significant figures, would you say? 3 sig figs? Does that feel appropriate? Does that feel appropriate? Yeah, I agree. 3 significant figures here. We've got 4 here, although MRs we don't typically count as part of our significant figure values because those are kind of a given, to be fair. And 100 centimeters cubed, that's a bit of a question mark because we can say that's 1 significant figure. We can say that's 3 significant figures, like, so we would just go with 3 significant figures. Yeah, great. Okay, are we ready to step it up 1 more notch? I think we are. We're doing, I mean, we're smashing these so far. Okay. Oh, I love a question like this. What is the total volume of gas? Oh, I need state symbols. Yikes. What is the total volume of gas produced when 4 grams of lead-2 nitrate decomposes at 35 degrees C and 101 kilopascals? Where do we start? Because we've got a bunch of information. We've got the mass of something, and then we've also got a temperature, we've also got a pressure, and we've also been given the gas constant R. So what does that suggest about where we're starting or what we're going to have to use in this calculation? Ooh, so George, we will need to do some conversion of units. We will need to do some ideal gas equation. You're absolutely right. But the first thing that we can do, what do we have enough information to calculate the moles for? Right? We've been told we're going to decompose 4 grams of lead-2 nitrate, and then we want to know the volume of gas. So the first thing really that we want is the number of moles, and we can calculate the number of moles of our lead-2 nitrate as our mass over MR. Oh gosh. Oh no. What's the MR for lead-2 nitrate? Oh, lucky I've got a periodic table at hand always. Again, if anybody gets this number before me, let me know. 207.2 plus 2 nitrogens, 14 plus 14 plus 6 oxygens. What did we get? I got 331.2. I really hope that's correct. If not, that'll be really embarrassing. Does anyone want to confirm or deny 331.2? Let's go with yeah. Let's go with that's fine. Yes? No? Maybe so? Feel free to argue with me. I make mistakes all the time, sometimes on purpose, sometimes not. Do we agree? Oh, George, good question. We ignore the big number. Great question. We do not include the coefficients when we're calculating MRs, right? The coefficients are for our stoichiometric relationships for us to figure out the molar ratios. But just to calculate the MR, we just take just one of them. Okay, thank you, Tanya. Wonderful. So we've got our moles of our lead to nitrate, thank you, as our 4 divided by 1.2 to get 0.0121. Okay. Now in the question, we want the total volume of gas. And you've already spotted its volume, its gas, and we've been given temperature and pressure. So we know we're going to have to use the ideal gas equation, PV equals nRT. And we know we're going to have to rearrange that to get volume. So V equals nRT over P. Now, before we put any numbers in, as George said earlier, before we put any numbers into our ideal gas equation, we need to make sure that we convert everything to the appropriate units, because the ideal gas equation units are often where students lose marks, right? Remembering the expression fine, units who sometimes not so fine. So let's do a little side quest and make sure that we've got all of our units where they need to be. So R is given to us. T should be in, of course, Kelvin. We've been given it in degrees C, so 35 plus 273. Thank you very much, George, which is, I don't know why I've put my calculator over on that side. Let's bring it back over here. Thank you very much. Okay, 35 plus 270. I should be able to do that in my head. 303,308. Thank you, Prisha. 308 Kelvin. And our pressure, what units do we want for pressure? What units do we want for pressure? Not kilopascals, but just pascals. Lovely. So we'll take our 101 times that by 1,000, and we get 101,000 pascals. Great. Now, and this is another point where mistakes are often made. What are we using for our moles? What are we using for N? What are we using for N? Who can spot what lots of students will do that you won't do because you're here? Oh, what should we use for our N? What are we using for moles? Not quite, natural scientist. Look at our state symbols. So far, we've calculated the number of moles for our lead-2 nitrate. So, but for our volume, we want the volume of gas. So we need to use our molar ratios, our stoichiometric relationships, to relate our moles of lead nitrate to our moles of gas. Now, we've got more than one gas here, but because all gases, as long as it's the same temperature and pressure, the same number of moles will occupy the same volume. So we can treat these gases all in one. So we can say that we've got 5 moles of gas, okay? Which means that our ratio of lead-2 nitrate to gas is a 2 to 5 ratio. 2 moles of lead-2 nitrate for 5 moles of gas. This is my dramatic pause for if there are any questions, right? If they say gas in general, it's probably because there's more than one gas and we need to treat them together. Thank you, ads, fantastic. And then, what do I want to say? Yes, and therefore, to convert our moles of lead-2 nitrate to our moles of gas using our molar ratio, we're going to take our moles of lead-2 nitrate, we're going to what we're going to do? Divide by 2 and then times by 5. Right? We divide by the first one and then multiply by the second. Lovely. So we've got 0.0302 moles of gas. No, George, the coefficients don't have to be the same on each side. No. But the total number of atoms of each element need to be the same on both sides, so it's balanced. But the coefficients, absolutely not. Right? As long as we've got the same number of PBs, Ns, and Os, we're balanced, we're fine, we're all good. Okay. Okay. Times 2 plus, okay. Natural scientist, if that's your way of doing it, absolutely. My brain, to be fair, it doesn't work like that, so I couldn't see it with the numbers that you put, but if it works the same, shout out to you, fantastic. No notes. Okay, but I would typically do it in this way, but if you have another way that works, and that's one of the nice things about A-level chemistry, especially when it comes to the quantitative stuff, there's more than one way to get to the right answer as long as it makes like physical and chemical sense, right? Now we've got our moles of gas and we've got our T, we've got our P. We can substitute everything in here. So our gas moles 0.0302. Our gas constant we've got in the question 8.31. Temperature 308 over our pressure 101,000. If anyone gets an answer, let me know. And also if you can tell me the units, even better. I've got 6. Sorry, no, I don't. That's a lie. That's a lie. I've got 7.65 times 10 to the minus 4. If we've used aunts for everything, if you've used the rounded values, you might get a slightly different number, right? But I've just used aunts. Okay. Thank you. Wonderful. Units are meters cubed. Great. Now, in this question, it didn't ask for what units, so we can leave it in meters cubed as long as we state those units. In terms of significant figures, what would be the most appropriate number of significant figures? Ooh, George, I'll come back to that question in a moment. I'll come back to that question in a moment. Let's look at the values given in the question. I think I want to see a couple more before I decide who I agree with. Okay. So we've got 3 significant figures over here. Over here for our temperature, 2 significant figures. For our pressure, 3 significant figures. The most appropriate is the least. So 2 wins. We can't be more precise than our least precise piece of data. So that would give us 7.7 times 10 to the minus 4 meters cubed. Least number of significant figures is what we choose. I know that our temperature ended up as 3, but in terms of what we were given 2. Is that clear? Are we happy with that? Or maybe not happy, but do we understand that? And then coming back to George's question, because it specifically just said gas, we can't include these 2 moles over here, right? We're only relating the number of moles of our lead 2 nitrate to our total number of moles of gas. And so that ratio is 2 to a total of 5. That's our ratio, right? We're not including our lead oxide, that's solid, that's not involved. Okay. How are we doing? We good? We ready for the next one? You're very welcome. Any questions here? Please do ask. Even if it's not like directly for this question, but it's still ideal gas related, then please do. Why divide moles by 2? So we're dividing the moles by 2. Well, we're not dividing it by 2. We're multiplying it by 5/2 because that's our molar ratio. Our ratio from our lead-2 nitrate to our gas is a 2:5 ratio. And so to use that 2:5 ratio, we divide by 2 and then times by 5. In the same way that if it was a 1:2 ratio, then we divide by 1 and then times by 2. If it was a 2:1 ratio, divide by 2 and then times by 1. So that's how we use our molar ratios to convert from the moles of one species to the moles of another, right? Because we've calculated the moles for our solid, but the question specified we wanted the volume of gas, which meant that in our ideal gas equation, we needed the moles of gas, not the moles of our lead-2 nitrate. We're doing good. Oh, I said natural scientist. That makes sense. That makes sense. So you did like a 1:2, and then a 2:1, and like combined them. Sure, absolutely. We did 4/331.2. Yeah, we did. Because 4, we were given enough information to calculate the number of moles of our lead-2 nitrate. Because in the question, we were given the mass of the lead-2 nitrate, and then from the periodic table, we can figure out the MR. We didn't have enough information to calculate the moles of the gas from the data given. So we had to use the moles of the lead-2 nitrate and then the molar ratio to give us the moles of the gas. Okay, Cupcake, this is an hour. But in the main course, and again, I'll talk about that a bit later on, in the main course for year 13, the lessons are an hour and a half. Okay, lovely. Okay, let's keep it pushing. Okay, this is a nice, ooh, okay. This is a nice quick one, but it's one that a lot of students don't know or were never taught. But this might be the easiest question in this whole workbook. Hopefully, just to make sure, because I forgot to remind you at the beginning, in the description of this video, you've got the workbook, the link that follows this PowerPoint exactly as we're going along it. So you can, and that's what you get for your lessons as well in the main course. So you can either print them in advance, or if you've got like a tablet-y kind of device, you can do it electronically so that for each lesson, you're not having to like write all the questions and do all the notes yourself. You can just annotate and write on the lesson itself as you're following it. Okay, so let's come to question 4. Assuming the temperature and pressure are the same, what is the minimum volume of oxygen required to burn 250 meters cubed of methane? And what is the maximum volume of carbon dioxide that can be produced? Why did I say this question is so easy? Well, the reason this question is so straightforward is because we can just use Avogadro's law, which, and we don't need to know this law off by heart, right? We don't need to be able to quote it, but what it essentially tells us is, similar to what we were saying before, as long as the temperature and the pressure are the same, right? 1 mole of any gas will occupy the same volume. 1 mole of any gas will occupy the same volume. So it doesn't matter what the identity of the gas is. We can just relate the volumes almost as if we're relating the moles. So what does that mean in practice? Yes, Ryan, the workbook will be available after the lesson. So, and some students do prefer to do this. They prefer to maybe just in the lesson, just kind of like stay with the lesson and chat, and then maybe fill in the workbook afterwards. That is absolutely fine. Literally, whatever works for you, because the lessons are recorded. So sometimes students want to re-watch the lessons and then do the workbook as they're watching it a second time. But then, like while they're live, just be here in the conversation. So whatever you want to do, whatever works for you. Okay. So if we have got 250 meters cubed of methane, then to figure out the volume of oxygen, we don't need to bring it down to moles, lovely natural scientists. All we need to do is use the molar ratios, and that will tell us essentially the volume ratios too. So because from methane to oxygen is a 1:2 ratio, that means our volume of oxygen that we would need minimum would be 500 meters cubed. Yes, lessons big are an hour and a half for Year 13. Not today, not for our trial, but for your typical main course lessons. They're an hour and a half, twice a week. And then you also get homework for every lesson, video solutions for every lesson, etc., etc. But I'll talk more about that in a bit, right? I'll give you all the details. What volume of carbon dioxide would we produce with that in mind? You tell me. What volume of carbon dioxide would we produce? Absolutely, thank you. Adds 1-to-1 ratio. So same volume, 250 centimeters, meters cubed, sorry, not centimeters cubed. Units are important. The units just stay the same, but we should include the units. Wonderful. Nice and straightforward. Okay, so don't forget your molar gas, your mo why can't I speak? Your molar ratios that also work as volume ratios if we're dealing with gases at the same temperature and pressure. Okay, let's get into the titrations. Is this what we've all been waiting for? A 10 centimeter cube sample of a bleach solution containing sodium hypochlorite is diluted to 250 centimeters cubed. 25 centimeters cubed of the diluted solution is titrated with 0.1 mole per dm cubed of sodium thiosulfate, requiring 18.5 centimeters cubed for complete reaction. Calculate the concentration of sodium hypochlorite in the original bleach solution. Oh, that's a lot of words. Now, with these sorts of titration calculations, when we're kind of transferring things from one vessel to the next, I think it can be quite helpful to draw just a mini diagram, right? Just like a little, not even a diagram, like a little cartoon strip so that you can track what's happening at each stage and then you can just follow the journey of the moles. Okay, so I'm going to do that and it's not going to take me very long. It might take me longer than it normally would because I'm talking through it, but it shouldn't take you that long if this is what you decide to do. So we're taking 10 centimeters cubed of our bleach, which has our NaClO. We're then diluting that to a total volume. Doesn't need to be pretty. My diagrams are horrific, but it doesn't matter. We're diluting that to 250 centimeters cubed. This is just a dilution, which means the number of moles are exactly the same, right? We've just added water. Same number of moles of sodium NaClO here and here. Okay, stop me at any point. Please, please, please stop me at any point that you lose me. Okay, don't wait until the end and then go, oh no, wait, I didn't get it from the start. At any point, please, 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 I love questions. If you understand it, then I'm happy. Okay, now from this sample, we are taking out 25 centimeters cubed, and then that's what we're going to carry out our titration against. And in our burette, we're going to have our sodium thiosulfate. And it says we needed 18.5 centimeters cubed of that. And we've got the concentration. Oh, hello. And we've got the concentration 0.1 mole per dm cubed. Okay. Now notice in this second transfer, as we took the solution out of our 25 centimeters cubed, so it's out of our 250 centimeters cubed to go to the 25, we took out a 10% portion, right? Which means that the moles of NaClO here are 10 times less than the moles in our larger solution. Okay, George, I do. I think it depends on the type of calculation. For calculations like these, like titrations, where they're saying we did this, then we took that, then we did blah, 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 blah. I like to draw it out to keep track of what's happening. Because then when you're calculating the moles, you can really easily visualize the journey of the moles. Joseph, this isn't a back titration. A back titration is when we react something with an excess of one thing, and then we take the remaining and then do a titration on that. Okay, there isn't a back titration in this lesson, but it will be in the main course and as I do some more content online as well. Okay, so based on all of this information, when in doubt, again, there's so much information here, but we're going to start by calculating the moles of whatever we can calculate the moles for. What do we have enough information to calculate the moles for here? What do we have enough information to calculate the moles for? We're dealing with solutions. So if we're dealing with solutions, thank you. We need concentration and volume. Appreciate, wonderful. We have got the concentration and the volume of our sodium thiosulfate, right? Because we were given the concentration was 0.1 moles per dm cubed, and we needed 18.5 centimeters cubed of that to react with our NaClO. So that's what we're going to start with. Moles of our sodium thiosulfate will be concentration times volume, which is, what's that, 18.5 over 1,000. And what do we get? What's that? 1.85 times 10 to the minus 3, I think. Right? That sounds about right. Yeah. Okay. Now it's just a case, again, of following that journey. Because we've now got the moles of our sodium thiosulfate, we know then how many moles of NaClO we had in that flask, right? And we get that, of course, from our molar ratios. Our ratio from sodium thiosulfate to our sodium hypochlorite is a 1 to 4 ratio, right? One of these for 4 of those. So we're going to take our moles and we're going to multiply that by 4. Prisha, good question. They will typically give you the equation unless it's the type of equation that you're meant to kind of know already. So when you do redox equations, often they'll ask you to write the half equations and the overall equation first, and then you use that for the titration. Or if it's a really straightforward like acid-base reaction, they might just expect you to write that equation and use it. If it's an unfamiliar equation, then they have to give you that equation. Okay? Okay. So we've got 7.4 times 10 to the minus 3 for our moles. Thank you, natural scientists. But, and here is a really important point, with these longer style calculations, and as we mapped out here, this is only the number of moles of our, oh, hello, why did I do that? Come back. This is only the number of moles in that 25 centimeter cube sample. But if we're trying to figure out what we had at the beginning, we need to now go back to figure out how many moles were in that original sample in that volumetric flask. So how many moles must have been in the 250 centimeters cubed? Well, it must be 10 times more moles, right? Are we happy with that? This is a really important point. If we took out 10% of the sample, there were only 10% of the moles in that final solution. So figuring out how many moles were in that first solution, we're going to have to multiply that by 10, which is the same as multiplying it by 250 over 25. Okay. This is my dramatic pause for any questions. I know this can sometimes be a bit of a tricky point, but drawing it out helps to make that, I think, hopefully a little bit easier to grasp. Okay, if there are no questions, then I'm going to keep going. So there are 10 times as many moles in this first solution in that volumetric flask than there were in that smaller one. Lovely. Now we've got the moles in here, and our final task is to calculate the concentration in the original 10 centimeters cubed. Now again, and I chose this question specifically, well, I kind of wrote it, I know. The number of moles of NaClO in here, as we mentioned before, is the same as the number of moles that were in our original solution. Because going from the original solution to the diluted solution, we only added water. The number of moles of NaClO did not change. I'll say that one more time. When we diluted that 10 centimeters cubed to 250 centimeters cubed, we only added water. So the number of moles of the NaClO did not change, right? It changed in the second step because we took some out for our titration, but it didn't change in that first step because we only added water, okay? So now we've got our moles in our original solution, and now, of course, we want our concentration in that original solution, which we established before is moles over volume. Moles, 7.4 times 10 to the minus 2. volume was 10 centimeters cubed. Yeah. 10 centimeters cubed, which we're going to divide that by 1,000 to give us 0.01 decimeters cubed. And then we get whatever our answer is. If anyone's got the answer already, by all means, tell me. What's that? That's really, 7.4 moles per decimeters cubed. That sounds dangerous. Oh dear. Oh, that's not enough significant figures. 7.40 is more appropriate. As our final answer. How do we feel about that one? Trickier, right? But your standard approach, and I'll even write it up at the top, when we're doing these sorts of titration calculations, your typical approach is going to be moles, ratio, moles, then scale, because if you've taken it out of a larger sample, and then do whatever it is they need you to do last. Here it was find the concentration. In other examples, it might be to do something else. I'm going to need a vibe check rather. How are we feeling? Do we feel okay about this one? Do we have any questions? Are we feeling confident? Are we feeling like, maybe I could be confident if I've got some more practice? Where are we? Should I give you, okay, Ryan, thank you. Feeling good. You can give me a number from 1 to 5. 5 being like yay, 1 being ooh. 5 for everyone. Yeah, okay, 4. Okay, that's pretty good. That's pretty good. Okay, wow. Now, we are quickly running out of time. Do you have another lesson straight after this? Because if you're willing to go a little bit over, then we can make sure that we do this last question too, because I do then also have some information to share about the main course if any of you wanted to sign up to, do this weekly and have some nice structure to your year 13 learning. Do we want to do this last question, or do we want to go straight to info about the course? Should I do a poll? I'll do a poll. Okay. One more cue, or just straight give me the info. But if we do one more question, bear in mind, it will mean that we'll go over a bit. I'm happy to go over if you're happy to go over, but I don't want to keep you if you don't want to stay. Okay, answer in the poll, please. In the poll. Okay. Okay. Wow, I'm loving the enthusiasm. Okay, let's do it. So far, 100% of you are saying one more question. So let's do one more question. Okay, let's finish strong. Let's do this one. Right. This type of question, so common, worth so many marks, right? Upwards of 6 calculation marks often, 6 marks rather, for this calculation, where we are trying to calculate the water of crystallization, so the value of X or N or whatever it happens to be. Now, whenever you see these questions where you're calculating the water of crystallization, the value of X, your go-to approach is going to be to calculate the MR. Okay? You want to calculate the MR of the whole thing, the whole hydrated salt. Because then from your periodic table, you can calculate the MR of the bit without the water. And then if you subtract those, then you end up with the MR of X waters. Then to calculate the value of X, you take your MR of your X waters and you divide by the MR of water, which is 18, and that gives you X. That's your approach, right? Use the calculation information to calculate the MR of the whole thing, and then from there you can figure out how much of that is water and how much of that is just the salty bit. Okay, the dot, so the X is water of crystallization, so it's like trapped water within the crystal. So it means for every 1 sodium carbonate formula unit, there are X water molecules like in that lattice surrounding it. Okay, and we want to calculate how many waters there are. What is X? So we want to calculate the MR. We know that MR, how is that going to be related to moles? Well, that's going to be mass over moles, because moles is mass over MR, and then you just rearrange. Okay, hopefully that's clear, but if not, as we work through this calculation, it's going to become even clearer. Now, through electrostatic, I would say. Okay, now we can draw this out, but I think there are fewer steps for this one, so maybe, no, actually, let's draw it out. We took our 3.2 grams and we dissolved that in water, and we made it up to 250 centimeters cubed. We then, just like before, took out a smaller sample of 25 and we did our titration of that against our HCl. And we've got, for the HCl, the concentration was 0.1 mole per dm cubed. And the volume that we needed for that was 22.5 centimeters cubed. Now we've got all of that, the rest, easy peasy, right? In theory. So we can start, we've got enough information to calculate the number of moles for our HCl, right? That's going to be our concentration times our volume, which is, what's that? 2.25 times 10 to the minus 3? I hope so. Yeah. Now we're going to use our molar ratios to figure out the number of moles of our sodium carbonate, which is the same as our moles of our salt, because it's the sodium carbonate bit that's reacting with the HCl. The ratio, 2 to 1. So we're going to take our moles and we're going to divide that by 2 and then times it by 1, but that's the same thing. And we get, oops, 1.125 times 10 to the minus 3. Now, what's the step? What do we need to look out for now that lots of people will miss, but you won't miss because you're used to these calculations now, or at least you're getting used to them. What should we then look out for? Hi, Yashi, back again. Yay. Hi, Yashi, how you doing? This was the number of moles that was in our titration, right? In our 25 centimeters cubed. But the original salt was dissolved in 250 centimeters cubed. So we need to do that scaling step. So the number of moles of our salt in that 250, which is what our original solid was dissolved in, is going to be multiplied by 10. Right? 250 versus 25. That is the step that a lot of students miss and then get kind of crazy answers and then start to panic because nothing makes sense. So always look out for that scaling. Did they take the sample for the titration out of a bigger pot? Okay, and if they did, then what is that scaling factor? Okay, right. Now we've got our moles. As we saw before, we need the MR of the whole salt, which is going to be mass over moles. So that's our 3.25 over 1.125 times 10 to the minus 2, right? And we get 288.9. Okay, but that's the MR of the salt with the water attached. If we want to figure out how much water was attached, we need to subtract that from, or we need to subtract rather the MR of just the Na2CO3, and that will give us the water. Okay, are we happy with that step? If not, please, please, please let me know. I'm trusting natural scientist. I'm trusting you and I'm using your value because it sounds about right. We get 182.9. So that's X multiplied by water. So to find out X, we're going to take our 182.9 and divide that by we'll divide the MR of water. Lovely. And we get, well, that's approximately 10, right? 10.2, but it's going to be an integer value. So X equals 10. Yeah. Feeling good? We love these calculations. There were so many marks. And if you can just track what's going on, then, I mean, it's not that bad. And if in doubt, and I always say this to my year 12s, to my year 13s, you are not allowed, right? Now that you've met me, you're making this promise with me too. You are not allowed to leave calculation questions blank because at the very least, you can get a couple of moles marks, right? Even if you're not sure what to do with it next, you can get a couple of marks from just calculating the moles, maybe use a ratio to figure out the moles of something else, but there's no reason to leave it blank. You can do something. Okay? Okay. Okay, thank you. Now, if you have enjoyed